Hello everyone, and welcome to this video in which we're going to be taking a look at a problem that has to do with Faraday's law of induction. So this is a very good example problem that deals with the very common type of problem that you would see when doing Faraday's law of induction. This question is actually taken from the AP Physics C Electricity and Magnetism exam. And it has three parts the way I have it here, and we're going to be going over each of them one by one. So we're going to go over what the problem is. So the problem says that we have a conducting bar of mass m that slides without friction. It slides down on two vertical conducting rails, which are separated by a distance L and joined at the top through an unknown resistance R. So basically what's happening is that we have these wires right here, and then we have a conducting bar that falls, that sort of, you can think of it as rolling on that wire, right? And there is no friction, so there wouldn't be any friction force acting on that bar as it rolls down. And then the bar maintains electrical contact with the rail at all times, and a uniform magnetic field is directed into the page. So that is referring to these lines that we have here. And remember, X means that the magnetic field is pointing into the page. And the important thing to note here is that the bar is observed to fall with a constant terminal speed V naught. And that is the speed here, right? So if you think about it, there must be forces that are balancing out, right? In order for us to have a constant speed, due to Newton's second law, the net force has to equal to 0, right? So just by looking at it, at the way everything is set up right now, if you draw the free body diagram on this bar, we're going to have an mg down. So if the mg is the only force that is pointing down, it would mean that it's accelerating downwards, right? So that tells us that there must be a force that is balancing it out, and it points to the towards the top, right? And that force turns out to be the magnetic force. So we're going to be taking a look at that in next slides, right? So here, the first part tells us to determine the voltage that is induced in the bar in terms of B, L, G, V naught, and M, right? So due to Faraday's law, right, we know that there will be a voltage induced whenever we have a change in magnetic flux, right? So you might be wondering how the magnetic flux is changing in this case. So if you remember, the magnetic flux is going to be equal to the magnetic field that we have dotted with the area vector that we have, right? So these are the two terms that contribute to the flux. So if any of these two change, either the magnetic field has to change or the area has to change. And there is also an angle involved too, because the magnetic flux is equal to BA cosine of theta. So any change in the angle would also result in a change in flux, but we're not dealing with that because we don't have a rotation here. So we don't have to worry about this cosine of theta term. So the only two terms that are influencing our total magnetic flux would be the magnetic field and the area. It tells us that the B is constant, so this is remaining constant. So the only way this magnetic flux can change is through a change in area, and this is in fact what we're seeing, right? As this bar falls down, if you look at the area that we're dealing with, excuse me, if you look at this closed loop, right, that completes our circuit. Here on the bottom side, we don't have a complete circuit because this is all empty, right? So the complete circuit, the complete loop that we have is the one on the top, like this. And it sort of goes through here as well. And as this bar falls down, so as this falls down, let's say in another second, it's going to be down here. You see the total area that the flux is going through is increasing, right? So as this bar falls down, there is going to be more magnetic field lines that are going to be going through that area. So the flux will increase, right? So if I were to continue this and write my equation in terms of the magnetic flux, which is B times A in this case, right? And I know that the B is constant, so I can take the B out. So the only way, so the only thing that remains there is the area, and that is what's changing. So I will be taking the time derivative with respect to area. So now, how is that area changing? Well, we know that as this falls down, this L right here is going to be constant. And this area, right, I'm going to say that the area is equal to this L. So this dimension right here is L. And this dimension right here, I'm going to call it X. Okay. So this L, as this bar falls down, the L is just going to be constant. So that L doesn't change. So here I'm going to write my area is equal to L times X. Okay. So that's what I'm going to do. I'm going to replace the A here with L times X. And again, like I said, as it falls down, the L is just going to be constant. So anything that is constant, I can take it out of the derivative, right? And sorry about the, I'm going to erase these. So yeah, so the L can come out, and what's going to be left inside is going to be the dx dt. And if you remember, what is dx dt equal to? Well, this is the rate of change of distance with respect to time, and I should tell you that it's going to be equal to the speed. And with what speed is it falling down? They already gave us v naught. So this, you can change it to v naught. And if we're dealing with a magnitude, you can take the magnitude, the absolute value of both sides, and that will be your answer for the voltage induced. All right, so that would be the first part. And then the second part is asking to determine the magnitude of the induced currents in the ball as it falls down. In terms of the V naught, B, L, G, and this is a typo, so this is already there. So V naught, B, L, and G. So we're going to go back to what we had, what I said initially in the problem, right? For this bar to maintain its constant speed, not only it has an mg down, but there must be a force that is balancing it. And that is the magnetic force. And for this, for the magnetic force, there are some equations, but the one that applies here, right, we have a bar that has a length L. So that should remind you of this equation right here, that the magnetic force is equal to I times the cross product of I, L, and B, right? So taking the cross products of I, L, and B gives us the magnetic force. Now, we know that because there was a voltage induced, there will be a current induced as well. And that's what we're trying to figure out, right? Now, the issue with this is that we're going to be having a cross product, right? And the way that the cross product works when it's written this way is that it also tells you the direction, right? We already sort of determined the direction just by analyzing the problem through its free body diagram. So we don't really need to know the direction of that force. So that way we can take the magnitude of both sides, and when you take the magnitude of the cross product, it can turn into BIL sine theta, right? Where theta is the angle between our magnetic fields and the currents induced. Now you might be wondering, what is that theta? Well, if these are the magnetic fields that are going into the page, and I have a current that is either going this way or this way, we're going to actually determine that too. But no matter what the direction of that current is inside of that bar, is always going to be perpendicular. So if you were to look at this like from this view, let's say your camera was here, you're going to be having magnetic fields that point down, and then you're going to be having a current that either points this way or this way, right? No matter what that is, it's always going to be, they're going to be perpendicular. So that theta, you can replace it with 90 degrees. And what is sine of 90 degrees? It's just simply going to be 1. So the force is going to be equal to BIL in this specific scenario. And we already determined that the magnetic force has to be balanced by the gravitational force. So it has to be equal to mg, and solving for I gives us mg over BL. So that is the answer to this part of the problem. You can also determine I in another way, which is going to help us in the next question, in the next part. So here we have to determine the resistance in terms of B, L, G, V naught, and M, right? So from the previous slide, we figured out that the I was equal to mg over BL. And a couple slides ago, we figured out the EMF induced was LBV naught, right? And by Ohm's law, we know that, let me switch my pen, is going to be V equals to IR. So if I divide both sides by R in this equation, my V over R is going to be my I, right? Well, this V is the same thing as epsilon, right? That is the induced EMF in this scenario. So I can divide both sides by R. And what does that give us? That gives us the I. So this is another expression for I. And these have to be equal because both of them are I, right? So we let them equal to each other in this case. And from here, we can easily solve for R. And this should be the answer for the resistance that is right here. The resistance in the wire. Now, let's do the right-hand rule to figure out if all the things that we said made sense, right? So let's see if what is the direction of the currents that is being induced, and what would the direction of the force be if we do the cross product, right? We're using the right-hand rule. So the way I like to do Faraday's law of induction with the right-hand rule is by 3 steps. First, I determine what is the initial flux, right? So here in this case, if I consider my area to be here, and I have magnetic fields pointing into the page, my initial flux is going to be into the page. So step 1 is into the page. Now what happens as this bar falls down? As this bar falls down, the area increases, right? So that means that the magnetic flux in that direction has to increase. So my next step is to determine what is the change in flux. So if the magnetic flux is increasing, right, and the original was into the page, and it's increasing, therefore the change must be also into the page. Now, we know by Lenz's law that they try to resist the change. So they would try to create a magnetic field that points in the opposite direction. So whatever I have in the second step, I do the opposite. If I have into the page, I do out of the page. And if you orient your right hand in such a way that your thumb points out of the page, so you can put your hands on the page and orient your thumb in a way that points out of the page. What you're going to notice is that the way your finger is going to be curling is going to be in a counterclockwise direction. So the current that will be induced is going to be in the counterclockwise direction. So in this direction. All right. And now we can figure out what is the direction of the force. Let's see if it makes sense with our analysis that we said that it has to be in the upwards direction, right? The way I like to do cross products with the magnetic force, what I like to do, I like to point my thumb, my right thumb, in the direction of the current inside of that bar. So I would point my thumb to the right. Then I would point my fingers in the direction of the field, right? Because I have like multiple fingers that sort of like, this is the way I remember it, because multiple fingers sort of stand for multiple field lines, and so that's the way I remembered it. So if the current goes to the right and my fingers point into the page, the direction that my palm faces in my right hand is going to be the direction of my force. So I can't physically show you, but if you orient your thumb to the right and your fingers into the page, you're going to see that your palm faces upwards. And so that is consistent with the force, with the magnetic force that we are set that is going to point upwards earlier. So everything is consistent. And that is pretty much it. All the problems have been solved. This is not a very difficult problem, but it's a very good conceptual problem. And it's important to know how this works, because a lot of the problems that you would see with Faraday's law of induction are similar, as they are all in this fashion. And I hope you enjoyed the video and learned something from it. And thank you for watching.